Hi, I'm Hyunwoo from KAIST. This is a collaborative work with Seung-hwan Baek, Giljun Nam, Min-H Kim. Now I'm going to present our recent work, Progressive Acquisition of SVBRDF and Shape in Motion. The acquisition of 3D objects appearance is a long-standing problem in the computer graphics and vision community. Traditionally, the acquisition of an object's 3D geometry and appearance can be achieved by capturing multiple images of different view and light direction. This acquisition setup has been extended to capture micro-scale appearance using multiple LED lights by Nam et al. Baek et al. Utilize a polarization filter in order to acquire both appearance and geometry more accurately. Although these methods estimate the object's appearance and geometry with high accuracy, building this system requires professional know-how and its cost is very high. While preserving detailed appearance of 3D objects, recent works try to improve the accessibility of imaging setup. Nam et al. Make use of multiple images captured by a mobile RGB camera with a flashlight to acquire an object appearance and geometry simultaneously. Woo et al. And Baek et al. Acquire an object's appearance and geometry using the conventional RGBD camera. After acquiring the geometry using a Kinect sensor, they make use of not only color images but also IR images to estimate the appearance. However, all these systems cannot capture moving object's appearance. The quality of reconstructed object is degraded when the object moves while capturing it. Several works have been proposed to tackle the object movement while capturing appearance and geometry. In the offline setup, Woo et al. Captured the geometry and also diffuse appearance of the moving object. Fifth et al. And Go et al. Captured the geometry and the appearance of the moving human by building a professional light stage setup. In the online acquisition setup, Do et al. Captured the geometry and appearance of a moving 3D object. This system requires multiple cameras with a professional capturing stage to acquire the appearance of a moving 3D object. Due to the cost required by this system, these systems were not approachable to the general users in our community. Recently, fusion-based approaches have been proposed to capture the geometry and appearance of a moving object with a practical setup using a single RGBD camera only. Newcombe et al. And Slavacheva et al. Captured the geometry of a moving object by estimating its motion field. Inmar et al. And Do et al. Improves the quality of the captured geometry and appearance by enhancing the motion accuracy by means of color information. Guo et al. Captured the geometry and diffuse appearance of a moving object under unknown lights. Progressive optimization of geometry and appearance enhanced the quality of results more accurately. However, none of these works can acquire spatially varying BRDF of a moving object. In this work, we aim to capture the geometry and appearance of a moving 3D object with a practical setup. In other words, we use a single RGBD camera to acquire the 3D object's geometry, its motion, and its SVBRDF, progressively updating them within a half second per frame by means of GPU. In the conventional RGBD camera, there are two different types of sensor to capture color and depth information. First, there is an active time-of-flight imaging module which captures depth information of scene. An infrared light module illuminates the scene with time modulation, and the infrared image sensor captures the reflected light over surface. Second, there is a color camera that captures color appearance of the scene within the visible spectrum. The color camera module captures the reflected light from the surrounding environment illumination. Suppose we know the geometry and appearance of a 3D object and the environment illumination for lighting. Using the rendering equation, we can render the object synthetically as shown on the right. Following the rendering equation, this rendered appearance of the object can be divided to the diffuse appearance and the specular appearance. In detail, we can formulate the object's appearance using spatially varying reflectance function. The reflectance function can be separated as the view-independent component and the view-dependent component. Diffuse reflectance is represented by the diffuse albedos, which determines the amount of energy evenly reflected in all directions. Specular reflectance is described by two different parameters. First, the specular albedo determines the amount of the reflected light reflected along the mirror direction with respect to the normal direction. Second, the specular roughness controls spread of the specular lobe. Although the diffuse and the specular albedo are spectrum-dependent components, the specular roughness parameter generally does not change across the spectrum. We use the word model to formulate our SVBRDF. To render the appearance of the object in real-world environment, we need light information where objects will be captured. To do so, we calculate the environment map before acquiring the 3D object. Specifically, we use 360-degree camera, like as Ricoh Theta, to capture the 360-degree images of the scene. Since dynamic range of color camera is not enough to capture the intensity of light, we change the exposure setting of the camera to get multiple exposure images. Using these various exposure images, we converted them into a high dynamic range 360-degree image. Furthermore, we project this high-resolution environment map to the spherical harmonics function to get its coefficient. Using the HDR environment map, we apply the rendering equation with a specular reflectance function. To render the specular appearance, we uniformly sample the environment map and accumulate specular samples with GPU acceleration. Diffuse appearance of the object can be computed more efficiently by using the spherical harmonics function rather than the applying rendering equation. Using spherical harmonics coefficient from level 0 to 2, we calculate diffuse shading with the surface normals of the object efficiently. Finally, by summing diffuse and specular reflections together, we render the final appearance of the object more efficiently. We employ the truncated sine distance function to progressively update the geometry of a 3D object. Each voxel stores the truncated sine distance value, which is distance between the surface and the position of voxel. These values can be computed in parallel using GPU. Later, the matching cube or raycasting algorithm is used to converting TSDF to an explicit geometry as mesh. However, this method can represent the rigid shape of an object only. Thus, to represent the deformed object in motion, we build a deformation graph which is associated with TSDF. Using the deformation graph, we first estimate the SVBRDF aware motion parameters of each deformation graph node that minimize the following energy loss term. The first term is about the geometric data loss. This term minimizes the point plane distance between the input frames and the estimated model at corresponding pixels. Then, the estimated geometry at the current frame can be formulated by employing the motion parameters with the geometry model at the previous frame. To prevent the motion field overfitted to noise depth input, we add a smoothness constraint as the following regularized term. Our final term is about the photometric data loss. The photometric data term constrains the motion parameters to make the appearance of the estimated model be consistent with the input color observation. Next, we estimate the appearance parameter of the target object using the estimated motion field. To relax the inverse rendering problem, we make use of the infrared point light and camera in the TOF camera module. We then estimate the specular parameters using infrared signals. Note that we capture input images indoor, where LED lights emit only visible spectrum, and thus the IR light in the TOF module works as a point light source. It allows us to estimate the specular parameters easily in the IR channel without relying on any sampling. Before estimating BRDF parameters, we need to convert the reflected infrared intensity into reflected light in the object's normal space as follows. We first linearize the IR channel by applying the inverse gamma correction. Then we remove shading by dividing it with the dot product of the surface normal and light vector. We remove the distance effect by multiplying the scalar distance between the surface point and the camera. Finally, we estimate the infrared spectrum specular parameters of each point with the half-angle buffer. The half-angle buffer of each surface point stores this reflected intensity value as the normal distribution function value at each surface point along the half-angle. To estimate the infrared spectrum specular parameters using half-angle buffer, we need to sample the various combination of half-angles and NDF values. However, we can only get one set of half-angles and NDF values of the surface point in one image. In our progressive acquisition setup, the number of specular samples is very limited. To estimate specular appearance properly, it requires lots of images to accumulate enough samples at the surface point. To get enough observation of the half-angle and NDF values within a few input images, we aggregate the observation samples per cluster in the fine-to-coarse manner. After merging them in the coarse level, we distribute the optimized parameter inversely in the coarse to fine manner. Specifically, we utilize the diffuse albedo of the object that we estimate the previous frame to cluster the object surface to the same material. First, we downsample these TSDF diffuse albedos to the deformation node by using the position of each node. Then, we apply the K-means clustering algorithm for clustering the diffuse albedos of nodes. We also merge all the half-angle buffer values of each node in the same cluster through the weighted average. Using the weighted average of half-angle buffer value, we estimate spectrum specular parameters for each cluster. Finally, to render the realistic image, we distribute this optimized parameter to each voxel. To handle this, we also generate the TSDF cluster to distribute specular parameters properly. The cluster index of each TSDF voxel inherits the cluster index of k nearest neighbor nodes, which has the smallest difference of the diffuse albedo values. Currently, our estimated specular parameters are based on the infrared spectrum. We need to adjust the IR specular appearance to the visible specular appearance. Since the specular roughness is invariant to the spectrum, we can use the specular roughness parameter directly estimated from the IR channel. However, in our rendering equation, the specular albedo term acts as a multiplier for the intensity of the specular image, which depends on the spectrum. The final step is to adjust the specular albedo parameter for RGB channels. To do this, we synthetically estimate the specular appearance in the color channels by subtracting the diffuse shading image from the original color image. Since we already acquired the specular parameters in the infrared channel, we can render the specular appearance under the RGB environment map using the infrared channel parameters. Using these two images, we can estimate the multiplier lambda by dividing the RGB channel specular appearance by the IR channel specular appearance. Here, note that we assume the object has dielectric surface and thus the RGB channel specular reflection is converted to a monochromatic channel. Finally, we adjust the specular parameter estimated from the IR channel to the RGB channel color using this lambda. Our final step of acquiring complete appearance parameter is to estimate the diffuse albedo of the 3D object. We minimize the following energy loss term to estimate the diffuse albedo. The color term minimizes the difference between the input color images and the rendered image with estimated parameters. To obtain this energy function efficiently, we make use of rendering equation with the estimated specular parameters. We render the specular appearance image with the given environment map. Our equation still holds when we subtract both input image and rendered images with the rendered specular image. After we subtract the specular image from the current input image, we can get a diffuse image as seen in the left. For the right-hand side of the equation, our rendered diffuse image can be reformulated as the spherical harmonics rendering function using the diffuse albedo and the input environment map. In consequence, we can reformulate the color term as the loss term of diffuse albedos. Note that we also increase the weight in optimization when surface normals are close to the view directions. The next term is temporal regularization term. Diffuse albedos do not change over time. Therefore, we add the temporal regularization term to constrain voxel albedos to be consistent with the previous frame's albedo. Our final term is a spatial regularization term. This term constrains the diffuse albedo of the central voxel to be consistent with neighboring voxels when their chromatics are similar with each other. Now we demonstrate our result of synthetically generated scenes. We applied synthetic deformation to the ground truth mesh and rendered to obtain the color images as shown in the top left. We added Gaussian random noise to generate realistic IR and depth images. The top right figure shows the estimated synthetic motion resulting using our method. With the estimated motion, our method reconstructs appearance and shape successfully as seen in the bottom left and bottom right images respectively. This video shows the result of our algorithm with a real-world 3D object, leather jacket. Our algorithm reconstructs the motion, appearance, and geometry of the clothes successfully while the jacket is deformed. We render the reconstructed jacket using our method in a noble view and noble light. While we are changing illumination, we demonstrate that our rendering results looks very realistic. This video demonstrates that our result of capturing a human in motion. Our algorithm successfully reconstructs the moving human model who wears the clothes of two different types of appearance. Also, we render the reconstructed human model in a noble view and noble light. We demonstrate that our results present very realistic appearance of the clothes under different illumination conditions. This video shows the result of another moving human who wears a specular leather bag. We can clearly see that our rendered specular reflection of the bag is virtually identical to the input video. Note that our appearance parameters are estimated progressively, so it becomes accurately. We compare the reconstructed results with the existing progressive acquisition method. While other methods cannot render the realistic specular appearance under noble light condition, our results demonstrate very realistic specular reflection of the bag. Our method is not free from limitations. Due to the low dynamic range of the IR receiver in an RGBD camera, the saturated pixel in the IR image resulting in inaccurate depth value as shown in this red circle region. When there is no geometry captured, our method cannot estimate appearance parameter properly. In addition, our spatial resolution of the reconstructed model is strictly restricted by the IR image resolution and TSDF. Due to the limited resolution of the TOF camera, our method cannot estimate high-frequency specular appearance sometimes. In conclusion, we have presented a novel material acquisition method that estimates SVBRDF, geometry, and motion simultaneously using a single RGBD camera. We have proposed a two-scale data structure that efficiently estimates material appearance. And also, we demonstrate that our appearance-aware motion estimation algorithm can improve the motion accuracy as well. Thank you.